Alright, recording a little bit of a two-slit experiment. I'm going to try turning the light off and see if that helps the image any. Kind of crappy. So, let's see, hopefully that's visible in some respect or another. So just going to try a couple of experiments. I can definitely see some interference pattern. Yeah, let's keep calling it that even though it's something else. So just trying to play with it a little bit, and just for the record, recording it probably for my own use. The real interesting thing is the effect I'm getting before the slit is an awful lot of diffraction. I'm just seeing how much, as I diminish or diffract the light more before it gets to the slit, how much that affects the resolution, the visibility of the pattern. It obviously helps to some extent, but yeah, it's quite an amazing pattern. So now I'm going to widen the slit a little bit on one side, see if it has any effect. Yeah, on the left side, so that's obviously, it seems like the right side image has gotten a little better. So I'm going to try to narrow it now. I have to get a magnifying glass, I think, but I can't see. Oh, get a flashlight. Shine a flashlight too, if that does anything. Some extra light, different light. Doesn't appear to do anything. Oh, you gotta point it at it. Look at that. Why isn't that a giveaway? No, it's 3 LEDs actually. Doesn't really give anything away. Yeah. So those are the images of the LEDs is showing up on the screen. The actual, you can actually see, if you really look at that, it's almost, you can see the bulbs in a horizontal position, which might be very interesting to see if that's what's actually happening. That is strange. I mean, they almost look, I mean, they are set in the thing as individual pedestal bulbs, but you should be able to see them because I'm shining them. Well, I am shining them horizontally through. But yeah, it's interesting. Anyway, back to what I was doing. Oh yeah, I need the flashlight to find the magnifying glass. Alright, here it is. Alright, so I'll try to do an adjustment on the slit without making a mess. And we'll see. Whoops. Yeah, I can't see though without the laser on it. I'll have to put the light back on apparently. Sorry, technical issues. It's, takes all kinds. Yeah, see, I can see a interference pattern quite well there. I should try this lensing. Yeah, so I can move the lens and actually change the focal position. Let's see what that does. And right there, you're sort of getting an idea of what, the middle impediment is showing up quite well there as an image, and you can sort of see that the straight line image maybe isn't. See, the one that has the little hook on it, I think, is actually the impediment's image. I think it's a human hair. I just say that, and it seems like that spur might be on the hair, but can't say for sure. But ooh, right there, that's a good pattern there. Yeah. Okay, so depending on the angle of the lens, I can change the pattern quite significantly. Well, anyway, sorry. I mean, that's the whole point of this video. Sorry, I'm only going to do this for about 5 or 10 more minutes, and then I'll get to the rest of the video. Like I said, most of this is for my own edification. But oh, yeah, that was a good one there. You know, I'll try to maybe grab some stills that are somewhat interesting, maybe. Anyway, okay, back to the project of correcting the slit width. So I'm going to try to make it as close as I can to as narrow as I can and still pretend like it's a slit. I mean, I'm doing this with like sliding pieces of paper, and so I don't know if I can get a really good straight ellipse without blocking off too much. That might be good, I don't know. It doesn't look, oh yeah, okay, that'll adjust the beam. I've moved the target, so that should be a little bit better. So that's not a bad pattern there. And so I can see that it's quite angled. And, you know, it's a little bit crooked, a little horizontal. So again, that's my hair refracting the light. Maybe I'll show that what I see on this side of the slit, which is sort of interesting. Just how much refraction there is. Anyway, well, it's a good experiment. It's I don't know, like I said, what the camera picks up. So we'll see what we can see. And yeah, so this is the target. And let's see if we can see that. Yeah, I don't know if you can or not. It's too bad it doesn't show up better in this camera. I'll have to try one of the other cameras. But you're getting lots of interference patterns. You know, lots of beams with breaks in them. So it's that bar pattern that is the, you know, that's the signature of the interference, wave interference signature. So this is without going through any slit, just reflecting off of different strands of hair. You know, it's interesting, requires some thought about what exactly is happening and why every single one has got a distinct and very visible bar pattern. Not every single, but all the dominant brightnesses of light all have a very distinct interference pattern. So anyway, enough of that. Alright, yeah, interrupting myself. Yeah, I made a mistake in my drawing, so I'm going to just do this segment over. So anyway, I'm responding to a guy who posted a link to this 1 photon in, 2 photons out thing. And, you know, it's a good thing to use in this as an example for why, you know, how they've sort of got this idea of what a photon is wrong, you know, in the sense that they draw them as single isolated objects, and they really aren't, and that's why this thing happens. And so it's, you know, if I do a reasonable job, I should be able to explain what I'm talking about. So what happens here basically is they shoot ultraviolet light in, and they get 2 photons out that you have a combined wavelength. You know, so it says here 2 photons can be created at the same wavelength with half the energy. So they're half as energetic, it would be called, and they're created as a consequence of this 1 photon going in. So 1 photon goes out, 2 photons come out. 1 photon in, 2 out. And so, yeah, that sounds weird if you're not thinking about it as an integral of time, and time is really important here. You know, the thing is that depending on how the light hits, it can produce 2 photons, you know, these different colors. I'm not sure whether it creates one each incident. You know, one would be one color and one would be this color, and one would, you know, they would be a pairing of the 2 different colors. Like these 2 would be the same, but the blue and the violet would go together. and I guess the red and the red might, well, they wouldn't add up. But anyway, this is my interpretation. What's wrong about the model of photons, photon, is that it's not really photon. It should be photons, or it should be a packet of quanta. So what a photon equals. So a photon shouldn't be thought of as a single thing. It's a packet of things, because you have to include its frequency. So like with radio wave, you could argue that the first piece of the wave shows up, and the second piece is 3 miles behind. You know, radio waves can be really long. So the end of the wave, which would have to be, you have to wait 3 miles for it. And the argument I would make is it's really 2 photons. The first one shows up, and then the second one shows up 3 miles later, shows up. And it's that wavelength, the distance between those, the period, that is really the definition of what we call a photon. You wouldn't be able to recognize it as a radio wave if there wasn't 2 of them. And so the photon isn't really carrying the wave. The photons are all the same. Radio wave photons are the same as microwave photons, are the same as visible light photons, are the same as cosmic ray photons. They're all the same photons. They're just separated by a different distance. And they don't travel. When we call them a photon, that is when we recognize them, when we identify them by a wavelength, we're not identifying a photon, we're identifying a pair, at least, of photons. So, in this experiment, what's really taking place is the ultraviolet light comes in, and let's say it's 300 nanometers wavelength. I don't know if that's right or wrong, but it's close. So that's the distance between the photons. So you could basically, theoretically, just add up the 300 plus 300 plus 300 to come up with a total of 900 nanometers in this total bundle of, say, 4 photons. So let's just say that's the bundle that really is significant. So it goes into this interaction with an atom and an electron, and what comes out, pencil stopped working, kind of in an opportune time. So what comes out is 2 photons, all right, where their angles are, you know, as they're half the energy at you know, the appropriate angle to be added up also. So the original has essentially been split both in direction and in energy. So you could argue that this 900 nanometer number is the number you have to end up in the end, and so you could have, you know, 2 450s come out, or perhaps a 500 and a 400, or a 600 and a 300. Yeah, which would be sort of interesting. That you'd actually get one piece of the, you know, that wouldn't work, right? I'm going to get myself in trouble again. If a 300 came out, so the point is these are just 2. So the point is you have 4 in the sense that that's your packet, and what you're releasing is just the minimum amount of photon as the 2 others. I mean, it could be 5, and then you would add extras here and have to add up that extra distance. But let's just go with this 3, 6, 9. I don't think it would count the 12. I mean, it can only count the 3 distances. So even though it's 4 photons, so, you know, I don't know whether that would change it significantly anyway. Anyway, I didn't want to get this confused, so I shouldn't have gone anywhere near this 300 one, because this, you know, 300 and 600 would add up to 900, but it wouldn't add up to, you'd be short energy. Right, so even though the wavelengths would match, the time would match. It doesn't seem possible to convert this packet into that arrangement. So if you made it 1200, I don't think that's going to change anything anyway, because then you could still have a 300, and then the option would be an 800, which seems too high. But anyway, it doesn't. This part doesn't really matter. I'm not going to do it a third time. But the point is, it's probably this even number. It probably has to be these two equal photons come out. That's the only way this works. So what happens is they're either green or I don't know how you could. I don't know how you could go higher. Again, if you make one 500, you make one 400. They're still different colors, so it works to that extent. But the 600, 300 just doesn't seem to work. I mean, this would be the 300 here would be one 300, and then how could this be a 600? That can't be a 600. Where here you can figure out that the 450 would be, half and half. Well, see, that's why we're somehow missing something in this length. This length is only accounting for 3 wavelengths, and we need 4. Okay, that's the problem. So it was my bad. I mean, you really have to count either the first. You either have to count. You have to count. Let's see. So it would be the first incidence would be between this, and then this and this would be 2, and this is 3. You have to count this distance, right? Because you don't count it. You don't count the head. You don't count the distance before this one. So you have to go all the way to the front of the next one and count that wavelength. Okay, so it is 1200. So this total has to be 1200. So now if you did a 300, let's see what it would be. Sorry, I don't like to have to change my math in the middle of a demonstration, but let's just see if it works. Alright, so we know that the half of the 1200 would be a 600 and a 600. And so that's something like, that's visible light in the reddish range, I believe. Redder than 500 would be in the middle, right? 500 or so, 550 let's say would be the middle range. So yeah, you'll be towards the red end. But anyway, but you could go with a 500 and a 12 would be 700. So that you could go kind of a violet and a 500, which would be getting redder, very red. So you go this reddish color and the violet as a combination. And then if you went to 400, so you're getting kind of bluish, that might be the more violet one. And then you would go 800, and then you go 300, and then 900. So 900 would be infrared. So you'd be so slow that you would be infrared, and invisibly so. That's that slow. It'd be invisibly red, and then you'd have an ultraviolet and an invisibly red would come out. But so it would still equal, still add up. Yeah, you'd have one ultraviolet and a infrared pair. Still have to think about that. I mean, it equals 12. It sounds like that should work, but it's somehow the inverse of. Oh, okay. Now I remembered. Sorry. What's happening is there's two of, there has to be 2 of one of them and 1 of the other. I mean, if they're that long in wave, now it just can't. It can't produce those. That's not a possible combination because the time is wrong. So yeah, you have to stay. You have to stay somewhere above this minimum wavelength. So it's never going to produce the infrared. That's why this infrared. It's infrared, so it's outside the range. Well, there shouldn't be an arbitrary range. So ignore that part. It's not outside that range. It just can't do it. It can only produce some kind of pair that's somewhere larger in wavelength than the creating source, and that the combination of those wavelengths has to add up to this total of 1200. Okay. Yeah, pretty sure. Anyway, I'll work on it some more. but that's the explanation, is that light's not a single photon, it's a packet of photons. Everything we see comes to us from multiple electrons, and we're just sent a packet of photons at a time, or bunches of them. And then they come from slightly different angles, slightly different electrons all the time. And so it's coming in a blotch of frequency, but it's coming so fast that we can't see any frame rate or any frequency change. And I don't mean the wavelength of the light is a different frequency, I just mean the packets come at different overlaps in frequencies. And our eye just doesn't perceive the nuance of it. It doesn't see the resolution that fine, so it just calls everything that comes from an area that photon, that string of photons, even though it's packets of photons. Yeah, that's enough of that. That's the explanation, mostly. It's correct. It's just there's something with that number I gotta fix. It gets kind of confusing because you have to think 900 nanometers, 1200 nanometers. You gotta think of bigger number, bigger space, which means, in a sense, less intensity. But it's the amount of time that's relevant. So I should do it more as a time equation. So all that really matters is that the wavelengths add up to the time that it takes 4 photons to go in and then 4 photons to come out, in the sense of 2 pairs. But those 2 pairs could carry 3 photons, which would change the wavelength by so instead of it being a 1-to-1 relationship to this 800 number, it would be this 800 number divided by 2, or 400. So yeah, so now that matches this 400, which is really interesting. So that's probably how it's done. And I still don't like that either. I like the same number going in as it comes out. So I have to work on that. Anyway, this is close enough. I'm not going to strain myself on it, but the point is that what's happening is that the stuff coming in is getting simply converted based on a time scale. So there's a group of ultraviolet coming in, and then there's little packets of the other stuff coming out, and it's if you take the energy of those wavelengths and add them up of what comes out, it equals what went in. That's the key point. That's the fact of the experiment. The fact that I don't draw it that way isn't the fact. But anyway, I'll work on it when I have time and such.